Okay, so we're going to do a couple of videos where we talk about parametric surfaces. Now, before we talk about what a parametric surface is, remember that we could describe a curve uh, as a parametric vector equation. So a curve can be described by the vector function r of t of one variable, and we're going to do everything in 3 dimensions. Hopefully that will make sense by the end of this. Okay, so any, if, x, y, and z are continuous, this is going to be some curve in R3 as t, let's say 0 less than or equal to t less than or equal to positive infinity. And really, we could just even go back to negative infinity or some subset, some interval. Okay, so the common examples, here are a few common examples. So let's look at the vector curve r of t equals cosine t 0 sine t. So what is this? And let's just say, well, let's just look at this. Cosine t 0 sine t. So what is this? Well, the z coordinate is always equal to 0, or sorry, the y coordinate is always equal to 0. The x coordinate is cosine t, and the y coordinate is sine t. So this is the x coordinate, this is the y coordinate. And so we see that in this case, x squared plus y squared is equal to 1. So the square of the x coordinate plus the square, whoops, that's not right. The square of the x coordinate plus the square of the z coordinate is equal to 1. Okay, so what does this mean? This as t goes from 0 to infinity or whatever, this is a circle in the xz plane. Okay, so this traces out a circle in the xz plane that's centered at x equals 0, y equals 0, and z equals 0. So it's kind of like the y-axis goes through it. It goes around the y-axis, a circle of radius 1 around the y-axis, okay? And I think if you understand that cosine t sine t is a standard parameterization for the circle, you'll have an easy time understanding why this is the circle in the xz plane of radius 1. Okay, and really for this, if we just said 0 less than or equal to t less than or equal to 2 pi, we'll get the whole circle. Okay, now if t can go from say 0 to infinity or whatever, then we just keep tracing out the same circle over and over again. So this is very similar to an example that we've seen in 2 dimensions. Okay, another familiar curve would be r of t is equal to cosine t sine t t. And we'll just say minus infinity less than or equal to t less than or equal to positive infinity. Okay, I remember this, we saw this earlier in the very beginning of the semester. This is a helix, and it goes around the z-axis. And finally, another very common example would just be a line. So if v naught and v, let's say, v naught and v are two vectors, r of t equals v naught plus tv is a line. The idea is that a curve is like a one-dimensional object. If you're a bug on a curve, you can only go in one direction, forwards or backwards. Okay, as opposed to when you're standing on the ground, you can go left, right, forwards, and backwards. So if you're a bug on a curve or whatever, or like a train on a train track, there's just one direction you can go, so it's one-dimensional. Okay, intuitively, we would call this one-dimensional. All right. Mathematically, we can call this one-dimensional because it depends on one parameter. It depends on one parameter that is the t, or it could be another variable like s. Okay, we're about to start talking about using vector equations to describe surfaces. Surfaces are 2 dimensions, so those are going to need 2 parameters. Okay, a surface can be parameterized by 2 variables. In this case, we're going to use s and t. The book uses u and v, but we're going to use s and t for these notes. Okay, so a surface can be parameterized with 2 variables. So what's going to happen here, and there's some parameter domain. So s and t lie in some parameter domain, which is in R2. Okay, so what this means is that for every point st in this domain, you're gonna use this vector to draw a dot. And as s and t vary through all of these points, this is a domain in R2, an open set in R2. As s and t vary through all of these points, you're gonna draw a different dot, and the end result is going to be a surface. Okay, again, a surface is two-dimensional, so it makes sense that we need to have two parameters. And in a way, the s and t are kind of like, we can kind of think about these as being coordinates, and we'll talk a little bit more about that in a later video. Okay, but let's look at one example. So consider the following surface with the parameterization r of st is equal to cosine s t sine s. And we'll just say 0 is less than or equal to t less than or equal to positive infinity. Sorry, that is not what I wrote down. We'll just say t goes from minus infinity to positive infinity, and same thing with s. Okay, so let's think about what this shape is. Well, again, like we saw before, this is the x-coordinate, this is the y-coordinate, this is the z-coordinate. If we fix a value of t, well, really for all values of t, this is going to be true. X squared plus z squared is equal to 1. And if we fix a value of t naught, then if we just fix a value of t naught, in other words, fix a value for the parameter t, and let s go from minus infinity to positive infinity, this is just going to be a circle in the y equals t0 plane, centered at x equals 0 and y equals 0. Okay, so this is going to be a circle in the y equals t naught plane, so a plane that's parallel to the xz plane, okay, and it's just going to be a circle of radius 1, okay? But notice that this is true for every t naught. So what happens then is that for every value of y from minus infinity to positive infinity, in other words, for every value of t from minus infinity to positive infinity, that is for every value of y from minus infinity to positive infinity, this shape is just going to be a circle. If we hold the t fixed and let s go, from really just 0 to 2 pi even, this is going to make a circle. So it's a bunch of circles. So this is a cylinder. It's a cylinder centered on the y-axis. Okay, now if we were to say make t go between 0 and 1, we'd get the part of the cylinder from the plane y equals 0 to the plane y is equal to 1. So it's like these planes cut off the cylinder, and we just get this section of the infinite cylinder. We just get the section of the infinite cylinder that goes from 0 to 1. So it's no longer an infinite cylinder. It just goes from 0 to 1. Okay, and similarly, we can also restrict, if we restrict the value of s, we're just going to get, well, depending on how we restrict it, we're just going to get part of the cylinder going in the round direction. So I don't know if that made sense, but let me say it again. Let's say we have 0 less than or equal to s less than or equal to pi over 2. This is the quarter cylinder in the region x is greater than or 0 and z is greater than or equal to 0. So instead of being the whole cylinder, it's just going to be a quarter of the cylinder. Okay, and so this is an introduction to parameterizing surfaces and one example of parameterizing surfaces. We're going to do more examples parameterizing surfaces in following videos.